Pick up any object near you. A cup, a phone, a book. It has mass. You can feel it resist when you push it. And you've probably always assumed that mass comes from stuff, from the material packed inside, from tiny building blocks stacked together like bricks in a wall. But here's the problem. The most fundamental particles in the universe, the electrons inside every atom of your body, have mass. They resist acceleration. They respond to gravity. And yet, as far as every experiment in physics can tell, they have no internal structure. No smaller pieces inside. No volume to fill with material. They appear to be points, dimensionless, with no interior at all. So where does their mass come from? If they're not little balls filled with smaller stuff, what is their mass? The answer forces us to completely rethink what mass actually means. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Pick up something near you. Anything. A glass of water, your phone, a book sitting on the table. Hold it in your hand and feel the weight of it. That sensation, that downward pull, that resistance when you try to move it quickly, that's mass. And for your entire life, you've had a perfectly reasonable explanation for why things have mass. They're made of stuff. They're filled with material. There's matter packed inside, and the more matter there is, the heavier the thing feels. A bowling ball is heavier than a tennis ball because there's more material crammed into it. A block of iron is heavier than a block of wood the same size because iron is denser, more tightly packed, more stuff per unit of volume. This intuition works beautifully in everyday life. It's how you learned to understand the physical world as a child. Heavy things have more stuff in them. Light things have less. Simple. But this intuition, as natural as it feels, is about to fall apart. Because when you zoom in far enough, when you get down to the most fundamental building blocks of the universe, you find something deeply strange. You find particles that have mass, real, measurable mass, and yet they don't appear to be made of anything smaller. They don't seem to contain stuff. They have no known interior, no smaller components packed inside. As far as every experiment in modern physics can determine, they are points, not tiny spheres with insides. Points. Dimensionless objects with no volume, no internal space to fill with material. And yet they have mass. They resist acceleration. They respond to gravity. They behave exactly as massive objects should. So if these particles aren't little containers filled with smaller things, what is their mass? Where does it come from? What even is mass if it doesn't require stuff? To answer these questions, we need to start from the beginning. We need to understand what mass actually is, not what we assume it is, but what physics tells us it is. And that journey starts with something you already know: atoms. Everything around you is made of atoms. Your body, the air you're breathing, the ground beneath your feet, the screen you're watching this on. Atoms are the building blocks of all ordinary matter. For a long time, going all the way back to ancient Greece around 400 BC, thinkers like Democritus imagined that if you kept cutting a piece of material in half, over and over, eventually you'd reach a smallest piece that couldn't be cut any further. He called these pieces atomos, meaning uncuttable. It was a brilliant guess, but it was just a guess. There was no way to test it at the time. For more than 2,000 years, the idea of atoms remained philosophical speculation. Nobody could see them. Nobody could prove they existed. It wasn't until the 1800s that chemistry started providing indirect evidence. Scientists noticed that elements always combined in fixed proportions by weight. 8 grams of oxygen always paired with 1 gram of hydrogen to form water. This made sense if matter came in discrete units with specific masses. But the real confirmation came in the early 1900s when experiments started revealing not just that atoms exist, but what they look like on the inside. And what they found was shocking. In 1897, the British physicist J.J. Thomson discovered the electron. He showed that atoms weren't the smallest things after all. They contained even tinier particles carrying negative electric charge. This was the first crack in the idea of atoms as solid, indivisible objects. If atoms had parts, they weren't truly uncuttable. Thomson proposed a model where the atom was a blob of positive charge with electrons embedded in it, like raisins in a pudding. It was a reasonable guess given what he knew, but it was wrong. In 1911, Ernest Rutherford performed one of the most important experiments in the history of physics. He fired tiny, fast-moving particles at a thin sheet of gold foil. If Thomson's pudding model was correct, these particles should have passed through with only slight deflections. The positive charge was supposed to be spread out evenly, like a soft cloud. Most of the particles would push through it easily, and most of them did pass straight through. But a small fraction of them bounced back at extreme angles. Some of them came almost straight back toward the source. Rutherford later said it was as if you fired an artillery shell at a piece of tissue paper and it came back and hit you. That result made no sense unless almost all of the atom's mass and all of its positive charge were concentrated in a tiny, dense core at the center. This was the nucleus, and it was astonishingly small. The nucleus of an atom is about 100,000 times smaller than the atom itself. Let that sink in for a moment. If you scaled up an atom to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the center of the field. Everything else, the entire rest of the stadium, would be empty space, occupied by nothing except the electric fields of the electrons orbiting at great distances relative to the nucleus. The atom, the basic building block of matter, the thing everything is made of, is almost entirely empty. The solid table you're leaning on right now is made of atoms that are overwhelmingly nothing. The reason the table feels solid isn't because atoms are packed tightly together with no gaps. It's because electromagnetic forces between atoms resist compression. Your hand doesn't fall through the table because electric fields push back, not because matter is truly solid all the way through. This was the first major blow to the idea that mass equals stuff. The stuff, the actual material, occupies a vanishingly small fraction of the space inside an atom. Most of what we think of as solid matter is empty. But let's keep going deeper. The nucleus itself has structure. It's made of protons and neutrons. Protons carry positive electric charge, and the number of protons determines which element an atom is. 1 proton makes hydrogen, 6 make carbon, 26 make iron, 79 make gold. Neutrons have no electric charge, but contribute to the atom's mass. Together, protons and neutrons account for more than 99.9% of an atom's total mass. The electrons orbiting far outside are incredibly light by comparison. A proton is about 1,836 times heavier than an electron. So almost all the mass in every atom, in every object you've ever held, comes from the protons and neutrons packed inside that tiny nucleus. For a few decades in the early 20th century, physicists thought protons and neutrons might be fundamental. They might be the bottom layer, the smallest building blocks with no internal structure. But starting in the 1950s and accelerating through the 1960s and 1970s, experiments at particle accelerators revealed otherwise. When physicists smashed protons together at high energies, they didn't behave like solid, structureless objects. They behaved as though they were made of even smaller things. These smaller things were eventually identified as quarks. Each proton contains 3 quarks, 2 up quarks and 1 down quark, bound together by particles called gluons that carry the strong nuclear force. Each neutron also contains 3 quarks, 2 down quarks and 1 up quark, again held together by gluons. So now the picture looks like this. You have an object, a book, a rock, a human body. It's made of atoms. Atoms are mostly empty space, with a tiny nucleus and orbiting electrons. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks and gluons. At every layer, as you zoom in, you find smaller components making up the larger structure. And at every layer, the mass of the larger thing comes from the mass and energy of the smaller things inside it. This feels natural. This feels like confirmation of our original intuition. Mass comes from stuff inside. The deeper you dig, the more stuff you find. But then you hit a wall. When you get to quarks and electrons, the pattern stops. As far as every experiment performed to date can tell, quarks and electrons have no internal structure. They don't appear to be made of anything smaller. They are what physicists call elementary particles, meaning they're not composite. They're not built from smaller pieces. They are, in the language of the current standard model of particle physics, fundamental. And here's where it gets strange. These fundamental particles are treated as point-like in our best theories. Not tiny spheres, not little balls, points. Objects with no spatial extent, no volume, no interior. When I say point-like, I need to be very precise about what that means. It means that in every experiment we've ever conducted, down to the smallest distances our most powerful particle accelerators can probe, these particles show no evidence of having any size or internal structure. We've looked, and we've looked hard. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, smashes protons together at energies that let us probe distances smaller than 1/10,000th the size of a proton. At those scales, quarks and electrons still look like points. No radius, no surface, no inside. Now, does that mean they are definitely literal mathematical points with absolutely zero size? Not necessarily. It means that at every scale we've been able to probe so far, they behave as though they are point-like. There could be structure at even smaller scales that we simply can't access with current technology. Some theoretical frameworks, like string theory, propose that what we see as point particles might actually be tiny vibrating strings or loops at scales far too small for current experiments to resolve. But as of right now, from the standpoint of established experimental physics, fundamental particles have no measured internal structure. They are point-like as far as we can tell. This is not just a minor technical detail. This is the central puzzle of this entire story. Because these point-like particles have mass, the electron, for example, has a very specific mass. It's tiny, about 9.1 times 10 to the negative 31 kilograms. That's an incredibly small number, but it's not zero. The electron has a definite, measurable, precisely known mass. It resists acceleration when you push on it. It curves space-time around it, just barely, because of its gravitational influence. It behaves exactly as a massive object should behave. And yet it has no known interior, no stuff inside, no volume to fill with material. So what is the electron's mass? Where does it come from? If you've spent your whole life thinking of mass as the amount of stuff in something, this creates a real problem. Because here's an object, the electron, with a real, measurable mass, and, as far as we can determine, there's no stuff in it. There's nothing inside. The thing that has mass is, at least as we currently understand it, not a container. It's not a box filled with smaller building blocks. It has no smaller building blocks. It's fundamental. This is the moment where we need to step back and ask a deeper question. What is mass really? Not what do we assume it is based on everyday experience, but what does physics actually tell us mass is? There are two ways mass shows up in physics, and both of them are about behavior, not about what something is made of. The first way is inertia. Mass is a measure of how much an object resists being accelerated. If you push on something and it barely moves, it has a lot of mass. If you push on something and it flies across the room, it has very little mass. Isaac Newton captured this in his second law of motion. Force equals mass times acceleration. If you apply the same force to two different objects, the one with more mass accelerates less. Mass is resistance to change in motion. This is sometimes called inertial mass, and it's what you feel when you try to push a heavy object across a floor. The heaviness, the sluggishness, the way the object seems to fight against your effort, that's inertia. That's mass making itself known. The second way mass shows up is through gravity. Mass generates gravitational attraction. Every object with mass attracts every other object with mass. The more mass something has, the stronger the gravitational pull it creates. This is what keeps you on the ground. Earth has a lot of mass, so it pulls you toward its center. The moon has mass, so Earth pulls on it and it pulls on Earth, keeping them locked together in orbit. This gravitational behavior of mass was first described by Newton in his law of universal gravitation, and later refined by Einstein in his theory of general relativity, where mass and energy curve the fabric of space-time itself. Here's the crucial point. Neither of these definitions of mass, inertial mass or gravitational mass, says anything about what the object is made of. Neither definition requires the massive object to have an interior, or a volume, or smaller parts inside. Mass is defined entirely by what something does, not by what it's built from. A particle that resists acceleration and responds to gravity has mass, period. It doesn't matter whether that particle contains smaller components or not. It doesn't matter whether it has spatial extent or not. If it resists being pushed, and if it gravitates, it has mass. This is a profound shift from everyday thinking. In daily life, mass and material go together so naturally that we treat them as the same thing. More material means more mass. Less material means less mass. And at macroscopic scales, at the scale of bowling balls and bricks and planets, this is completely true. A brick has more mass than a feather because it contains more atoms, and those atoms are heavier on average. The connection between stuff and mass works perfectly at human scales, but at the fundamental level, the connection breaks. You reach a layer of reality where particles have mass, but aren't made of stuff, where mass is a property that a particle simply has, not because of what's inside it, but because of something else entirely. The question then becomes, what is that something else? Before we get to the answer, let's make sure we understand just how well established this picture is. The idea that elementary particles are point-like isn't some fringe hypothesis. It's one of the most rigorously tested claims in all of science. The standard model of particle physics, which describes all known elementary particles and 3 of the 4 fundamental forces, treats electrons, quarks, and other fundamental particles as point-like objects. This model has been tested to extraordinary precision. Its predictions match experimental measurements to 10, 11, sometimes 12 decimal places. In some cases, the standard model's predictions are the most precisely confirmed predictions in the entire history of science. The magnetic moment of the electron, for example, has been measured and predicted to an agreement of better than 1 part in a trillion. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. This kind of precision tells us that the mathematical framework treating electrons as point-like is capturing something very real about nature. These aren't rough approximations, these are exact descriptions, accurate to more decimal places than almost any other measurement in science. And the electron isn't alone. All the fundamental particles in the Standard Model, the 6 types of quarks, the 3 charged leptons, which include the electron, the muon and the tau, the 3 neutrinos, and the force-carrying bosons like photons and gluons, all of them are treated as point-like. None of them have measured internal structure. They all have specific masses, except for photons and gluons, which are massless, and those masses range enormously. The electron has a very small mass. The top quark, the heaviest known fundamental particle, has a mass roughly 340,000 times larger than the electron. That's a huge range. But all of them, light or heavy, appear to be point-like. Their masses vary dramatically, but their internal structure, as far as we can measure, doesn't exist. Now, let me be very clear about something important. When physicists say a particle is point-like, they're making an experimental statement, not a metaphysical one. They're saying that within the resolution of our best experiments, these particles show no substructure. They're not saying they've proven for all time that no substructure exists at any scale. Physics has been surprised before. In the 1890s, atoms were considered fundamental. Then Thomson discovered the electron, and Rutherford discovered the nucleus, and suddenly atoms had parts. In the 1950s, protons and neutrons were considered fundamental. Then deep inelastic scattering experiments at Stanford in the late 1960s revealed quarks inside them. Each time physicists probed smaller scales with higher energy experiments, they found new layers of structure that nobody had expected. Could the same thing happen again? Could quarks and electrons turn out to be made of even smaller things we haven't yet detected? It's possible. Some theoretical frameworks propose exactly this. Preon models, for example, suggest quarks and leptons might be built from even more fundamental particles. String theory suggests point particles might actually be tiny vibrating strings at scales too small for any current experiment to resolve. These are legitimate theoretical ideas, but so far there's no experimental evidence supporting any of them. Until someone builds an accelerator powerful enough to probe even smaller distances and actually finds substructure, the experimental verdict stands. Quarks and electrons are point-like as far as we can tell. So let's sit with this for a moment, because this really is the heart of the matter. You have particles like the electron, fundamental objects with no measured internal structure, no spatial volume, no smaller parts inside. And yet they have a definite, measurable mass. The electron's mass isn't zero. It isn't vague or undefined. It's one of the most precisely measured quantities in all of physics. We know the electron's mass to about 11 significant figures. This particle, which has no known interior, has one of the best known masses in nature. How is that possible? How can something that isn't made of smaller stuff have mass? To start seeing the answer, let's compare the electron to something we understand better. Consider a proton. A proton also has mass, about 1,836 times more mass than an electron. But the proton is not point-like, it's composite. It's made of 3 quarks held together by gluons and the strong nuclear force. The proton has internal structure. It has a measurable size, a radius of roughly 0.84 femtometers. That's extraordinarily small, less than 1/1,000,000,000 of a millimeter, but it's not zero. The proton is a tiny object with an inside, and that inside is a seething, dynamic environment of quarks and gluons constantly interacting and exchanging energy. Here's what makes the proton so fascinating for our discussion. The 3 quarks inside it, 2 up quarks and 1 down quark, have their own individual masses, but those individual quark masses are tiny. The combined mass of the three quarks accounts for less than 2% of the total mass of the proton. Less than 2%. That means more than 98% of the proton's mass comes from something other than the intrinsic mass of the quarks inside it. The proton's mass is not simply the sum of the masses of its parts. Something else is contributing the vast majority of the mass. Something we'll explore in depth very soon. For now, the important point is this. Even for composite particles like the proton, mass isn't just about counting the pieces inside and adding up their individual weights. Mass is more complicated than that, more subtle, more interesting than simple bookkeeping. But for the electron, the situation is even more dramatic. The proton at least has parts. It has quarks and gluons interacting in complex ways, and even though the quark masses don't account for most of the proton's mass, there's clearly a rich internal world contributing energy and dynamics that ultimately show up as mass. The electron has none of that. No parts, no internal dynamics, no substructure contributing energy, and yet it still has mass. This tells us something profoundly important. Mass does not require internal composition. Mass does not require spatial volume. Mass does not require smaller pieces inside. Mass is not the same thing as being made of stuff. This might be the single most important conceptual shift in all of modern physics when it comes to understanding what matter really is. For thousands of years, going back to the ancient Greeks and running through Newton and the classical physicists, mass was essentially synonymous with amount of matter. The more matter you had, the more mass you had. Matter was stuff, tangible substance, things you could in principle touch and divide. Mass told you how much of that substance was present. But modern physics has revealed that this picture, while perfectly useful at human scales, is incomplete at the deepest level. Mass isn't the amount of stuff. Mass is a property. It's something particles have because of how they interact with certain features of the universe, not because they're containers filled with material. Think of it this way. Consider electric charge. An electron has a negative electric charge. That charge is a property of the electron. Nobody asks what the charge is made of, or where inside the electron the charge is stored. It's not made of anything. It's not stored anywhere in particular. Charge is simply a property that the electron possesses. It's a measurable quantity that determines how the electron interacts with electromagnetic fields. You don't need to look inside the electron to explain its charge. The charge simply is. Mass works the same way. Mass is a property, not a substance. The electron has mass the way it has charge. The mass determines how the electron interacts with gravitational fields and how it resists acceleration. You don't need to look inside the electron to explain its mass, because mass isn't something stored inside. It's a property arising from something else entirely. But what? What gives the electron its mass if not internal stuff? That question sat at the center of particle physics for decades, and answering it required one of the most profound theoretical insights in the history of science, an idea that took nearly 50 years from initial proposal to experimental confirmation. An idea that fundamentally changed what we mean by empty space, by vacuum, by the very arena in which the universe plays out. Because it turns out that space itself isn't empty. Even a perfect vacuum, a region with absolutely no particles in it at all, isn't truly empty. It's filled with something invisible, intangible, and present everywhere in the universe. Something that every massive fundamental particle is constantly interacting with, every single moment of its existence. And that interaction is where mass comes from. To understand this, we need to talk about fields. Not the green kind with grass and cows, but the physics kind. The invisible structures that permeate all of space and give rise to the forces and particles we observe. Because the universe, at its deepest level, isn't made of tiny billiard balls bouncing around in emptiness. It's made of fields. And those fields are where the real story of mass begins. We started this journey with a simple question. How can a particle have mass without being made of stuff? We've seen that mass doesn't require internal structure. It doesn't require spatial volume. It doesn't require smaller parts. Mass is a property, measurable through inertia and gravity, that doesn't depend on what a particle is made of internally. But we haven't yet explained where that property comes from for particles that have no internal composition at all. That explanation lies in one of the most remarkable discoveries in the history of physics, a discovery about the nature of fields, the structure of supposedly empty space, and the mechanism by which the universe assigns mass to the particles that inhabit it. The universe has a way of giving mass to point-like particles, and it has nothing to do with filling them with material. It has to do with a field that fills all of space itself. To understand where mass comes from for particles that have no internal structure, we need to fundamentally rethink what the universe is made of. Because the picture most people carry around in their heads, tiny particles zipping through empty space like billiard balls bouncing around on an infinite table, is wrong. Not slightly wrong, fundamentally wrong at the deepest level. The universe isn't made of particles floating in emptiness, it's made of fields. A field, in physics, is something that has a value at every point in space and time. It's not confined to one location. It's spread out everywhere. You already have some intuition for fields even if you don't realize it. Temperature is a kind of field. At every point in the room you're sitting in right now, there's a temperature. It might be warmer near the heater and cooler by the window, but at every single point in the room, temperature has a definite value. You don't have to place a thermometer everywhere to know the field exists. The temperature is there whether you measure it or not. Now think about something more physical. Think about a magnetic field. If you hold a magnet near a compass, the compass needle swings to align with the magnet's field. That field isn't a physical substance you can see or touch. It's invisible, but it's undeniably real. It exerts force on objects that interact with it. It has strength and direction at every point in space around the magnet. Michael Faraday introduced this idea of fields in the 1830s, and it was revolutionary. Before Faraday, physicists thought forces acted at a distance, that a magnet somehow reached across empty space and grabbed the compass needle. Faraday proposed something different. The magnet creates a field that fills the space around it, and the compass needle responds to the field at its own location. The field is the intermediary. It's the thing that carries the influence from one place to another. James Clerk Maxwell took Faraday's idea and turned it into precise mathematics in the 1860s. He showed that electric fields and magnetic fields are really two aspects of the same thing, the electromagnetic field. And he showed that light itself is a ripple in this electromagnetic field, a wave propagating through it. Light isn't a substance, it's a disturbance in a field, a vibration in something that permeates all of space. Now take this idea and extend it to its conclusion. Modern physics tells us that everything in the universe, not just electromagnetism, but everything, is a manifestation of fields. There's an electromagnetic field pervading all of space. There's an electron field pervading all of space. There are quark fields, one for each type of quark. There are fields for every fundamental particle. According to quantum field theory, which is the mathematical framework underpinning all of modern particle physics, these fields are the truly fundamental entities. Not particles, fields. So what are particles then? Particles are excitations of these fields. They're ripples, disturbances, localized vibrations in a field that extends everywhere. Think of a perfectly calm lake. The water fills the entire basin. That's the field. Now drop a pebble in and watch the ripple spread outward. That ripple isn't separate from the water. It is the water, moving in a particular pattern. The ripple is an excitation of the lake's surface. If you could somehow freeze the ripple and isolate it, you'd have something that looks like a distinct object, a little bump moving through the water. But it's not a separate thing. It's a pattern in the underlying field. An electron is like that ripple. The electron field fills all of space, invisible and intangible. When the field is excited in a particular way, when it vibrates with a specific pattern, that excitation is what we detect and call an electron. The electron isn't a tiny ball sitting in the field. It is the field, locally disturbed. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. Every particle you've ever heard of is an excitation of its corresponding quantum field. This changes the picture dramatically. Empty space isn't really empty. Even when you remove every particle, every atom, every speck of dust, and every photon of light, you still have the fields. They're still there, filling every point in space, sitting quietly in what physicists call their ground state, their lowest energy configuration. They're not doing nothing in this ground state. Quantum mechanics ensures that even in the ground state, fields fluctuate slightly. There's a minimum level of quantum fuzz that never goes away. But no particles are present. The fields are calm. No ripples above the quantum minimum. Now, most of these fields, when they're in their ground state, their calm resting state, have a value of 0. The electromagnetic field in empty space, far from any charges or magnets, is 0. The electron field, when there are no electrons around, is 0. 0 is the default, the quiet state, the background hum with no ripples. But there's one field in the universe that breaks this pattern. One field whose ground state, whose resting value, even in completely empty space, is not 0. This field sits at a non-zero value everywhere in the universe. Every cubic centimetre of space, whether it's in the vacuum between galaxies, or inside your body, or at the centre of a star, this field is there, and it is not 0. It's always on. It never switches off. It pervades everything at every moment. This is the Higgs field. And it is unlike any other field in the Standard Model. The Higgs field was proposed theoretically in 1964 by several physicists working independently. Peter Higgs, working in Edinburgh, published a landmark paper describing a mechanism by which particles could acquire mass through interaction with a field that fills all of space. Around the same time, François Englert and Robert Brout in Brussels arrived at essentially the same idea through a different approach. Other physicists contributed related work in the same period. The core insight was the same across all of them. If you introduce a field that has a non-zero value everywhere, particles that interact with that field behave as though they have mass. But what does it actually mean for a particle to interact with the Higgs field and acquire mass? This is the heart of the mechanism, and it deserves careful explanation. Remember what mass is. It's not stuff inside. It's resistance to acceleration. It's how much a particle fights back when you try to change its motion. A massive particle is hard to speed up, hard to slow down, hard to deflect. A massless particle like a photon has no resistance to acceleration at all. It's born moving at the speed of light and can never move at any other speed. Now imagine a particle moving through space. In the picture we've been building, space isn't empty. It's filled with the Higgs field, which has a non-zero value everywhere. The particle interacts with this ever-present field, and that interaction is what gives the particle its inertia. The interaction with the Higgs field is what makes the particle resist changes in motion. The stronger the interaction between the particle and the Higgs field, the more mass the particle has. The weaker the interaction, the less mass. And if a particle doesn't interact with the Higgs field at all, it has zero mass. This is exactly what we observe. Photons don't interact with the Higgs field. They pass through it without coupling to it at all. And photons are massless. They travel at the speed of light and have zero rest mass. Electrons interact weakly with the Higgs field. They couple to it, but not very strongly, and electrons have a small mass. Quarks interact more strongly with the Higgs field, and they have larger masses. The top quark, the heaviest fundamental particle we know of, interacts extremely strongly with the Higgs field, and its mass is enormous by particle physics standards, roughly 340,000 times heavier than the electron. The pattern is consistent. The strength of a particle's coupling to the Higgs field determines how much mass that particle has. You might wonder whether there's an analogy that can help make this more intuitive. Let me offer one, but with a clear warning that all analogies for quantum field theory have limits. Imagine a large room filled with people standing around at a party. This room full of people represents the Higgs field, present everywhere, never switching off. Now imagine someone completely unknown walking through the room. Nobody notices this person. Nobody interacts with them. They glide through the crowd effortlessly, without resistance. This person is like a photon. No interaction with the field, no mass, moving freely at maximum speed. Now imagine a very famous person walking through the same room. Everyone wants to talk to them. People crowd around, slowing them down, making it harder for them to change direction or speed up. Every step requires more effort because the crowd keeps engaging with them. This person is like a top quark. Strong interaction with the field, lots of mass, lots of resistance to any change in motion. The analogy captures something real. Mass comes from interaction with the Higgs field, and different particles interact differently. But the analogy also misleads in an important way. It makes it sound like the Higgs field creates friction or drag, as though it's slowing particles down. That's not what happens. The Higgs field doesn't slow particles down. A massive particle moving through space at a constant velocity will keep moving at that velocity forever, just as Newton's first law says. Nothing slows it. The Higgs field doesn't resist motion, it resists changes in motion. It gives the particle inertia. The difference is crucial. Friction would make a moving particle gradually stop. Inertia keeps a moving particle going and makes it hard to change what it's doing. The Higgs field creates inertia, not friction. So throw out the image of wading through thick soup or pushing through a crowd that grabs at your sleeves. Those images imply drag, and drag is wrong. Instead, think of it this way. Before a particle interacts with the Higgs field, it has no inertia. It's like an object with zero mass, infinitely easy to push around, impossible to keep still. The moment the particle interacts with the Higgs field, it suddenly has resistance. It pushes back when you try to accelerate it. It has weight. It has heft. Not because anything was put inside it, not because it absorbed material from the field, but because its relationship with the field changed its fundamental behavior. Mass is a relational property. It comes from the interaction between the particle and the ever-present Higgs field. It doesn't come from stuff being added to the particle's interior. Now here's something beautiful about this mechanism. The reason the Higgs field has a non-zero value everywhere isn't random. It's a consequence of the field's own properties. Early in the universe's history, shortly after the Big Bang, the Higgs field actually did have a value of zero everywhere, just like the other fields. All particles were massless. The universe was a hot, dense soup of massless particles, all moving at the speed of light. Try to picture that for a moment. Every particle in existence moving at light speed in every direction. Nothing could slow down. Nothing could clump together. Nothing could form structure of any kind. Without mass, there is no inertia, and without inertia, nothing resists being pushed around. Particles couldn't bind into atoms because binding requires particles to settle into stable configurations, and you can't settle into anything when you're moving at the maximum speed the universe allows. The early universe was brilliant and chaotic and utterly formless. A blaze of massless particles screaming through space at 300,000 kilometers per second with no possibility of becoming anything more complex. No atoms, no molecules, no stars, no planets, no life. Just light, in every direction, forever. But as the universe expanded and cooled, something happened. The Higgs field underwent what physicists call a phase transition. Think of water cooling below its freezing point. Above freezing, water is liquid. Below freezing, it crystallizes into ice. The molecules rearrange into a new configuration. Something similar happened to the Higgs field. Below a certain temperature, the zero value became unstable. It was like a ball balanced on top of a hill. As long as the temperature was high enough, quantum fluctuations kept it there. But as things cooled, the ball rolled down into a valley. The field settled into a new, lower energy state, a state where its value was not zero. Once the Higgs field settled into this non-zero state, particles that interacted with it suddenly acquired mass. Before the transition, electrons were massless, zipping around at light speed like photons. After the transition, electrons coupled to the now non-zero Higgs field and gained their characteristic mass. They slowed down below light speed. They gained inertia. They became the electrons we know today, particles with a small but definite mass that determines how they behave in atoms and chemistry and biology. This transition happened very early in the universe's history, a tiny fraction of a second after the Big Bang. But its consequences shaped everything that followed. Without the Higgs field settling into its non-zero state, no particle would have mass. Electrons would be massless. They couldn't be bound into atoms. Without atoms, there would be no chemistry. Without chemistry, no molecules, no water, no DNA, no life. The Higgs field having a non-zero value everywhere in the universe is one of the prerequisites for our existence. For decades after the theoretical proposal in 1964, the Higgs field remained exactly that, theoretical. Physicists were confident in the mathematics. The Higgs mechanism explained beautifully why some particles have mass and others don't. It fits seamlessly into the broader framework of the Standard Model. It solved deep theoretical problems about the masses of the W boson and Z boson, the particles that carry the weak nuclear force. Without the Higgs mechanism, the mathematics of the weak force produced nonsensical infinities. With it, the calculations worked perfectly. But confidence in mathematics isn't proof. Physics demands evidence, and the most direct way to confirm that the Higgs field exists would be to detect its associated particle. Remember, every quantum field has a particle associated with it. The electromagnetic field has the photon. The electron field has the electron. The Higgs field should have its own particle, a ripple in the Higgs field itself. This particle is the Higgs boson. Think of it this way. The Higgs field fills all of space at a steady, non-zero value. It's calm, uniform, the same everywhere. But if you inject enough energy into the field at one point, you can create a localized disturbance, a ripple. That ripple is the Higgs boson. It's not the thing that gives other particles mass. The field itself does that. The boson is just evidence that the field exists. Finding the Higgs boson would be like dropping a rock into a lake you can't see. You know the lake is there because things interact with it. But if you can make a splash, a visible ripple, That's direct proof the water is there. Creating a Higgs boson requires enormous energy. The particle is very heavy by particle physics standards, with a mass of about 125 giga-electron volts. To create it, you need collisions at energies high enough to excite the Higgs field into producing a ripple. For decades, particle accelerators simply weren't powerful enough. The Higgs boson was predicted to exist, but remained beyond experimental reach. That changed with the Large Hadron Collider at CERN near Geneva. This machine, a circular tunnel 27 kilometers in circumference, buried underground beneath the border of France and Switzerland, accelerates protons to nearly the speed of light and smashes them together. The collisions produce energies sufficient to create particles that haven't existed freely since the first moments after the Big Bang. On July 4, 2012, two independent experimental teams at the Large Hadron Collider announced they had found a new particle consistent with the Higgs boson. The discovery was a triumph. It confirmed that the Higgs field is real. Not just a mathematical trick, not just an elegant theoretical idea, but a real, physical feature of the universe. A field that fills all of space, has a non-zero value everywhere, and gives mass to elementary particles through their interaction with it. Peter Higgs and François Englert received the Nobel Prize in Physics in 2013 for their theoretical prediction nearly 50 years earlier. Robert Brout, who had worked alongside Englert, had passed away before the discovery, and the Nobel is not awarded posthumously. Now, there are some common misconceptions about the Higgs boson and the Higgs field that are important to clear up. First, the Higgs boson does not fly around giving mass to other particles. You sometimes hear it described as the particle that gives mass to everything, as though it's distributing mass like a delivery service. That's not how it works. The Higgs boson is just a ripple in the Higgs field. It's unstable and decays almost immediately after being created. The thing that gives mass to elementary particles is the field, not the boson. The field is always there, everywhere, all the time. The boson is just the evidence we use to confirm the field's existence. Second, the Higgs mechanism does not explain all mass in the universe. This is a critical point, and one that many popular accounts get wrong. The Higgs mechanism explains the mass of elementary particles, the fundamental particles of the Standard Model. It explains why the electron has its particular mass, why the quarks have their particular masses, why the W and Z bosons are massive, while photons are not. These are the intrinsic masses of elementary particles, and the Higgs field is responsible for all of them. But here's the thing. The mass of elementary particles, the mass generated by the Higgs mechanism, accounts for a surprisingly small fraction of the mass you experience in daily life. The objects around you, your body, the chair you're sitting on, the planet beneath you, are made of atoms. The mass of an atom comes overwhelmingly from its nucleus, and nuclei are made of protons and neutrons. Protons and neutrons are not elementary particles. They're composite. They're made of quarks and gluons. And the mass of a proton, the thing that accounts for the vast majority of the mass in every atom, and therefore in every object you've ever touched, does not come primarily from the Higgs mechanism. The quarks inside a proton have intrinsic masses generated by their interaction with the Higgs field, but those quark masses are tiny. The two up quarks and one down quark inside a proton have a combined mass that accounts for less than 2% of the proton's total mass. Less than 2%. That means more than 98% of the mass of every proton in your body has nothing to do with the Higgs field giving quarks their mass. It comes from somewhere else entirely. Let me say that again because it really matters. If you weigh, say, 70 kilograms, the Higgs mechanism is directly responsible for only about 1 kilogram of your mass. 1 kilogram out of 70. The other 69 kilograms, the overwhelming majority, comes from a completely different source. This is one of the most stunning facts in all of physics, and most people have never heard it. The Higgs field explains why elementary particles have mass, but it does not explain most of the mass you encounter in everyday life. The mass of your body, of the Earth, of the Sun, of nearly everything made of ordinary matter, comes predominantly from something else. So what is that something else? What accounts for the other 98%? The answer takes us deep into the interior of the proton, into one of the most violent and energetic environments in the known universe. A place where massless particles generate almost all of the mass we experience, where the energy of interactions between quarks and gluons becomes the weight you feel when you step on a scale, and where one of the most famous equations in history, the equation that connects energy and mass, reveals its full power. Because the mass of the proton, the mass that makes up most of the mass of everything around you, doesn't come from stuff packed inside. It comes from energy. Pure energy, bound and confined and forbidden from escaping. And that energy, through Einstein's most famous insight, is mass. The Higgs field gives elementary particles their intrinsic masses, but the mass you actually feel, the mass of the physical world, the mass of atoms and molecules and rocks and oceans and stars, that mass has a different origin. An origin so counterintuitive that even physicists took decades to fully appreciate it. We've now seen two layers of the answer to our central question. Mass doesn't require internal stuff. For elementary particles, mass comes from interaction with the Higgs field, a field that fills all of space and gives particles inertia through coupling, not through filling them with material. The particle doesn't need an interior, it needs a relationship with a field. But the story doesn't end there. Because the mass generated by the Higgs field is only a small piece of the total mass in the universe, the rest of the mass that dominates everything you touch and everything you see, comes from a source that's even more surprising. And understanding that source requires us to look inside the proton and confront one of the deepest truths in modern physics. The truth is that mass and energy are the same thing. We ended with a startling fact. The Higgs field, for all its importance, accounts for less than 2% of the mass of a proton. And since protons and neutrons make up more than 99.9% of the mass of every atom, and atoms make up everything you've ever touched, this means the Higgs mechanism is directly responsible for only a tiny sliver of the mass you encounter in daily life. The vast majority of the mass of your body, of the ground beneath you, of the planet, of the stars, comes from somewhere else. So let's go inside the proton and find out where. The proton is one of the most important particles in nature. Together with neutrons, protons make up the nuclei of atoms, and those nuclei account for almost all the mass of ordinary matter. A proton has a mass of about 938.3 mega-electron volts in the energy units physicists use, which is roughly 1.67 times 10 to the negative 27 kilograms. That's unimaginably small by everyday standards, but it's enormous by particle physics standards. It's nearly 2,000 times heavier than an electron. The proton is what gives atoms their heft. Now, as we discussed, the proton isn't fundamental, it's composite. Inside every proton are 3 quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force. The strong force is carried by particles called gluons, just as the electromagnetic force is carried by photons. These quarks and gluons form the proton's internal structure, a structure we can actually probe with high-energy experiments at particle accelerators. Here's where things get deeply strange. Let's add up the masses of the quarks inside the proton. An up quark has an intrinsic mass of roughly 2.2 mega-electron volts. A down quark has an intrinsic mass of roughly 4.7 mega-electron volts. Those are the masses generated by the Higgs mechanism, the masses these quarks carry because of their interaction with the Higgs field. Two up quarks at 2.2 each give 4.4 mega-electron volts. One down quark at 4.7 gives 4.7. Add them together and you get about 9.1 mega-electron volts. That's the total quark mass inside the proton from the Higgs mechanism. The proton's total mass is 938.3 mega-electron volts. The quarks account for about 9 mega-electron volts. That's less than 1%. Read that again. The actual material, the quarks themselves, the building blocks inside the proton, contribute less than 1% of the proton's total mass. Some estimates put it a bit higher, around 1 to 2%, depending on how you define the quark masses at different energy scales, but the basic picture is the same. The quarks are almost negligible. The overwhelming majority of the proton's mass, more than 98% of it, comes from something that is not the quarks themselves. So what makes up the other 98%? Where does all that mass come from, if not from the material inside? The answer is energy. Pure energy. The energy of the strong nuclear force binding the quarks together. The energy of gluons being exchanged between quarks at incomprehensible speeds. The energy of quantum fluctuations inside the proton that create temporary quark-antiquark pairs popping in and out of existence. All of this energy, contained within the tiny volume of the proton, is the proton's mass. This is where Einstein's most famous equation becomes far more than a bumper sticker. E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us something profound. Energy and mass are not different things. They're the same thing measured in different units. Mass is a form of energy. Energy is a form of mass. They're interconvertible, related by a conversion factor of c squared, the speed of light multiplied by itself. When Einstein published this result in 1905, it was revolutionary. Before Einstein, mass and energy were considered completely separate quantities. Mass was the amount of stuff in something. Energy was the ability to do work, to push things, to heat things, to make things move. They had different units, different definitions, different roles in physics. Einstein showed they were the same thing all along. And this equivalence isn't just theoretical. It's been confirmed experimentally countless times. Nuclear reactors work because of it. When uranium atoms split apart in a nuclear reactor, the total mass of the fragments is slightly less than the mass of the original uranium atom. That missing mass hasn't disappeared. It's been converted to energy, released as heat, which boils water, turns turbines, and generates electricity. The amount of energy released is the missing mass times c squared. It's a tiny amount of mass, but c squared is an enormous number, about 9 times 10 to the 16 in standard units. A tiny bit of mass converts to a tremendous amount of energy. The reverse process also works. Energy can become mass. In particle accelerators, when protons collide at near light speed, the kinetic energy of the collision can create entirely new particles that didn't exist before. The energy transforms into mass. The Higgs boson itself was discovered this way. Nobody put Higgs boson material into the collider. The energy of the collision was sufficient to create the particle from nothing but energy. Mass from energy. E equals mc squared, working in reverse. Now, apply this to the proton. Inside the proton, quarks are held together by the strong nuclear force, which is carried by gluons.
The strong force is, as its name suggests, extraordinarily strong. It's the strongest of the four fundamental forces, roughly 100 times stronger than the electromagnetic force, 100,000 times stronger than the weak force, and about 10 to 38 times stronger than gravity. The strong force is what holds quarks together inside protons and neutrons, and it's what holds protons and neutrons together inside atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons that would otherwise blow every nucleus apart. Gluons are fascinating particles. Like photons, they are massless. A gluon has zero rest mass. It gets nothing from the Higgs field. And yet gluons are responsible for generating the vast majority of the proton's mass. This sounds paradoxical. How can massless particles generate mass? The answer is that gluons carry energy, enormous amounts of energy, and that energy, through E equals mc squared, is mass. Inside the proton, quarks are constantly exchanging gluons. Not occasionally, not now and then, but constantly, furiously, at rates and energies that are almost impossible to visualize. The strong force doesn't work like the electromagnetic force, which gets weaker as you move farther apart. The strong force does something entirely different. At very short distances, when quarks are extremely close together, the strong force is actually quite mild.
Quarks can move around relatively freely when they're very near each other. This property is called asymptotic freedom, and its discovery was one of the great achievements of 20th century physics. The story of that discovery is worth telling, because it illustrates just how surprising the strong force turned out to be. In 1973, three physicists, David Gross and Frank Wilczek, working together at Princeton, and David Politzer, working independently at Harvard, performed calculations that shocked the physics community. They were trying to figure out how the strong force behaves at very short distances, inside the proton, at the scale where quarks interact. Every other force in nature gets weaker with distance. Electromagnetism gets weaker as you move charges farther apart. Gravity gets weaker as you separate masses. This is intuitive. Things far away pull on you less than things close by. The expectation was that the strong force would work the same way, that it would be strongest at very close range and get weaker as quarks moved apart. Gross, Wilczek and Politzer found the exact opposite. The strong force gets weaker at short distances and stronger at long distances. This was completely unprecedented. No other known force behaved this way. It was like discovering a spring that goes slack when you compress it and gets tighter when you stretch it. The physics community initially struggled to accept the result because it contradicted deep intuitions about how forces should work. But the mathematics was clear. The calculations were rigorous. And when experimentalists tested the predictions at particle accelerators, the results matched perfectly. Quarks inside a proton, when probed at very high energies, which correspond to very short distances, behaved almost as though they were free particles. They barely interacted with each other at close range. But at longer distances, the force between them grew relentlessly, eventually becoming so strong that separation was impossible. This discovery earned Gross, Wilczek and Politzer the Nobel Prize in 2004. But more importantly for our story, asymptotic freedom explains something essential about the proton's mass. Because the strong force is weak at short range, quarks inside the proton can move around with tremendous kinetic energy. They're not pinned in place. They're zipping around at significant fractions of the speed of light. And because the strong force is strong at longer range, all that energy is permanently confined. The quarks can never escape. The energy can never leak out. It's trapped, bound, locked inside the proton forever. And all of that trapped energy, the kinetic energy of fast-moving quarks and the field energy of the gluons mediating the force between them, is what we measure as the proton's mass.
To understand just how thoroughly this energy is trapped, consider what happens when you try to pull quarks apart by force. Think about a rubber band. When you stretch it a little, the restoring force is small. Stretch it more, and the force pulling the ends back together grows. The strong force is similar in spirit, though the physics is completely different. The farther quarks get from each other, the harder the strong force pulls them back. The gluon field between them doesn't spread out and weaken like an electromagnetic field does. Instead, it concentrates into a narrow tube, almost like a string or a rope connecting the quarks. The energy stored in this gluon tube increases as you stretch it. What happens if you pull hard enough? What if you really try to yank a quark out of a proton? You might expect the string to eventually break, freeing the quark. And in a sense, the string does break. But here's the astonishing thing. When the gluon tube snaps, the energy stored in it is so enormous that it creates new particles. A quark-antiquark pair materializes from the energy of the broken string. E equals mc squared again. The energy becomes mass. You started with one proton and tried to pull out a quark. You end up with the original proton, or something like it, plus a new particle, typically a meson, made from the newly created quark-antiquark pair. You haven't freed a quark. You've created more particles. This is called quark confinement. Quarks can never be isolated. You can never pull a single quark out of a proton and hold it up by itself. Every attempt to separate quarks generates enough energy to create new quarks. The strong force will not let go. It would rather create new matter from pure energy than allow a quark to exist alone. This has been confirmed by decades of experiments at particle accelerators around the world. Nobody has ever observed a free quark. They always appear in groups, bound together by gluons, confined inside composite particles called hadrons, which include protons and neutrons. The energy involved in all of this, the constant exchange of gluons between quarks, the tension in the gluon field, the quantum fluctuations that create temporary quark-antiquark pairs inside the proton, is enormous relative to the masses of the quarks themselves. The interior of the proton is not a calm, static arrangement of three quarks sitting quietly. It's a seething, turbulent, incredibly dynamic environment. Quarks zip around at significant fractions of the speed of light. Gluons are constantly being emitted and absorbed. Pairs of quarks and antiquarks appear from the vacuum and vanish again in tiny fractions of a second. The energy density inside the proton is staggering. Let me try to give you a sense of just how extreme the conditions inside a proton really are. At any given moment, the proton doesn't just contain three quarks. It contains a seething cloud of virtual particles. Quantum mechanics allows energy to fluctuate, and inside the proton, those fluctuations are violent. Quark-antiquark pairs appear from the vacuum, exist for unimaginably brief instants, and then annihilate. Gluons split into more gluons. Those gluons split again. At any given snapshot, the proton might contain dozens of virtual particles, in addition to the three permanent quarks that give the proton its identity. Physicists call the three permanent quarks valence quarks, and the temporary ones C quarks. The C is always churning. The energy density inside the proton, the amount of energy packed into its tiny volume, is almost beyond comprehension. A proton has a radius of roughly 0.84 femtometers. That's less than 1/trillionth of a millimeter. If you calculate how much energy is crammed into that space, it works out to roughly 10 to the 35 joules per cubic meter. To put that in perspective, if you could somehow fill 1 cubic centimeter, about the size of a sugar cube, with matter at the energy density of a proton's interior, it would contain more energy than the total annual energy consumption of the entire planet. And not by a small margin, by many orders of magnitude. Physicists have even recreated conditions similar to the proton's interior, briefly, in particle accelerators. When heavy ions like gold nuclei are smashed together at nearly the speed of light, at facilities like the relativistic heavy ion collider at Brookhaven, the collision produces a quark-gluon plasma, a state of matter where quarks and gluons are briefly freed from their confinement. For a fleeting instant, the temperature reaches trillions of degrees, hotter than the core of any star. This plasma existed naturally in the first microseconds after the Big Bang, before the universe cooled enough for quarks to condense into protons and neutrons. Recreating it in the laboratory confirmed that the picture we've been describing is correct. The interior of every proton in your body is a relic of the most extreme conditions the universe has ever known. All of that energy is the proton's mass.
When you step on a bathroom scale and it shows you a number, almost all of that number comes from the energy of the strong force inside the protons and neutrons in your body. It doesn't come from the intrinsic mass of quarks. It doesn't come from the Higgs mechanism in any direct sense. It comes from massless gluons carrying energy, from kinetic energy of quarks moving at enormous speeds, from the energy stored in the gluon field that binds everything together. Energy that, through Einstein's equivalence, is indistinguishable from mass. Let me put this in personal terms to make sure the magnitude sinks in. If you weigh about 70 kilograms, roughly 154 pounds, here's how that mass breaks down at the fundamental level. About 69 kilograms of your mass comes from the energy of the strong force inside the protons and neutrons in your atoms. About 1 kilogram comes from the Higgs mechanism giving quarks and electrons their intrinsic masses. A vanishingly small fraction comes from the electromagnetic energy holding electrons in orbit around nuclei. The details shift depending on how precisely you do the accounting, but the basic picture is stark. You are overwhelmingly made of energy, not stuff. This is so counterintuitive that it deserves emphasis. When you pick up a heavy object and feel its weight, you're feeling energy. When you struggle to push a car that's stuck in the mud, you're pushing against inertia created by energy bound inside protons and neutrons. When the Earth pulls you toward its center with gravitational force, that gravity is responding primarily to the energy of the strong force inside every atom in your body and every atom in the planet. The stuff, the quarks themselves, contribute almost nothing to the gravitational pull. The energy does nearly everything. Think about how strange this is. Gluons are massless. They get absolutely nothing from the Higgs field, yet they are the dominant source of the proton's mass. The mass of the proton, the particle that accounts for most of the mass of everything you see around you, comes primarily from the energy of massless particles. Mass from masslessness. Weight from weightlessness. Substance from something that has no substance of its own. How do we know all of this? How confident are physicists in this picture? Extremely confident. The theory that describes the strong force and the behavior of quarks and gluons is called quantum chromodynamics, usually abbreviated to QCD. It was developed in the 1970s, and it has been tested extensively ever since. The mathematics of QCD is well established. Its predictions have been confirmed by experiments at every major particle accelerator in the world. But calculating the proton's mass from QCD is extraordinarily difficult. The equations of QCD are nonlinear and incredibly complex. Unlike quantum electrodynamics, the theory of the electromagnetic force, where you can often calculate answers using relatively straightforward approximation methods, QCD at the energy scales inside a proton resists such approaches. The strong force at these scales is too strong for the standard approximation techniques to work.
You can't calculate the proton's mass with pencil and paper in any simple way. Instead, physicists use something called lattice QCD. This is a computational approach where you simulate the equations of QCD on a discrete grid, a lattice, of points in space and time. You put the quarks and gluons on this lattice, apply the rules of QCD, and let the simulation run. You compute the energy of the system from first principles, using only the known quark masses from the Higgs mechanism and the known strength of the strong force. Nothing else. No adjustable parameters, no fudge factors, just the fundamental theory applied on a supercomputer. This might sound straightforward, but the computational challenge is immense.
The quark and gluon fields fluctuate at every point on the lattice, and the finer you make that grid, the more accurate the result, but also the more computing power you need. Early lattice QCD calculations in the 1970s and 80s were crude, using coarse grids and simplified approximations. They gave rough estimates, but nothing precise. It took decades of algorithmic improvement and exponential growth in computing power to get accurate results. By the early 2000s, supercomputers had become powerful enough to run lattice QCD simulations with grids fine enough to resolve the proton's internal structure. These simulations used millions of processor hours on machines occupying entire buildings. Each calculation required tracking the behavior of quark and gluon fields at millions of lattice points, evolving them through thousands of time steps and averaging over countless random configurations to extract a final answer. It was one of the largest sustained computational efforts in the history of science. The results are remarkable. Lattice QCD calculations, running on some of the most powerful supercomputers in the world, reproduce the proton's mass to within a few % accuracy. Starting from quarks that contribute less than 2% of the mass and gluons that contribute 0% of the mass, the calculation generates the full proton mass, 938.3 mega-electron volts, purely from the energy of the strong force interactions. The mass emerges from energy. It is confirmed computationally from first principles. This is one of the great triumphs of modern theoretical physics. We understand where the proton's mass comes from. We can calculate it, and the answer is not stuff. The answer is energy. Now let me contrast these two sources of mass, because keeping them straight is essential to understanding mass in the modern sense. Elementary particle mass comes from the Higgs mechanism. The electron, the quarks, the W and Z bosons, these particles interact with the Higgs field, and that interaction gives them their intrinsic mass. This mass is a property that each particle carries individually because of its coupling to the Higgs field. The particle doesn't need internal structure for this. It doesn't need to be composite. It doesn't need parts. The mass comes from a relationship between the particle and a field that fills all of space. This is the mass we explored when we discussed the Higgs field. Composite particle mass, the mass of protons, neutrons, and all the larger structures built from them, comes overwhelmingly from the energy of internal dynamics. The energy of quarks moving at high speed, the energy of gluons being exchanged, the energy stored in the strong force field. All of that energy, confined inside the particle, contributes to its mass through Einstein's equivalence of energy and mass. The quark's own Higgs-derived masses are a minor contribution. The energy is what matters. These two mechanisms are completely different in origin. One involves coupling to the Higgs field. The other involves the dynamics of the strong force. One gives mass to point-like objects that have no interior. The other gives mass to composite objects through the energy trapped inside them. Both are real. Both produce genuine, measurable, physical mass. And both contribute to the mass of the objects around you, just in vastly different proportions. There's a deep philosophical implication here that deserves attention. For centuries,
dating back at least to Newton and arguably much further, mass was understood as the amount of matter in something. Newton defined it essentially this way. Mass was quantity of substance. It told you how much stuff was present. And this definition worked brilliantly for centuries. It works perfectly well for engineering, for construction, for cooking, for everything at human scales. More stuff means more mass, period.
But quantum chromodynamics and the Higgs mechanism together reveal that this classical definition, while practically useful, is fundamentally incomplete. Mass is not the amount of stuff. Most of the mass of ordinary matter comes from energy, not from the intrinsic mass of constituent particles. The quarks contribute almost nothing. The gluons are massless. The energy does almost everything. What you call stuff is mostly energy wearing the mask of substance. Now here's a question that might be nagging at you. If most of the proton's mass comes from energy, does that mean mass is somehow not real? Is mass an illusion? Is it just energy pretending to be something it's not? Absolutely not. The mass of the proton is completely real. It's as real as any quantity in physics. When a proton resists acceleration, it's not pretending to resist, it genuinely resists. The inertia is real. When a proton generates a gravitational field, that field is real. Other objects respond to it. The gravitational effects of mass that comes from energy are identical to the gravitational effects of mass that comes from any other source. Einstein's general relativity doesn't distinguish between them. Mass is mass. It curves space-time, it creates gravity, it resists acceleration. Regardless of whether that mass originated from the Higgs mechanism or from strong force energy, the physical effects are identical. Saying mass comes from energy is not saying mass is fake. It's saying mass is more fundamental and more interesting than we thought. It's saying the universe has multiple ways of generating this property we call mass, and some of those ways don't involve filling a container with material. The universe is more creative than our intuition expected. Consider an analogy. Imagine you discover that the weight of a loaded backpack comes not from the objects inside, but mostly from springs that are compressed and loaded with tension. The springs are massless in this thought experiment, but they store enormous energy. That stored energy, through some physical mechanism, contributes weight. The backpack is still heavy. It still pulls down on your shoulders. The weight isn't fake, but its origin is different from what you assumed. You assumed the weight came from the stuff inside. It actually comes from the energy stored in the springs. The experience of heaviness is the same. The cause is different. That's the proton. The proton is heavy. It resists acceleration. It gravitates. All of those effects are completely real. But the cause of its mass isn't quarks filling up the interior like marbles in a jar. The cause is energy, bound energy, confined energy, energy that cannot escape because of the nature of the strong force. And this isn't some special feature of protons. Neutrons work the same way. A neutron contains one up quark and two down quarks, held together by the same gluon-mediated strong force. The quark masses inside a neutron add up to roughly 11 mega-electron volts. The neutron's total mass is about 939.6 mega-electron volts. Once again, the quarks contribute less than 2%. The rest is strong force energy. Every nucleus in every atom inherits this property. The nucleus of a carbon atom contains 6 protons and 6 neutrons. The mass of that nucleus comes overwhelmingly from the strong force energy inside each of those 12 particles. The same is true for oxygen, iron, calcium, every element in the periodic table. Every atom in your body, every atom in the Earth, every atom in the stars carries mass that is dominated by the energy of the strong force,
not by the intrinsic masses of quarks. This means the Earth's gravitational pull on you, the thing that keeps you from floating off into space, is generated overwhelmingly by energy, not by the material substance of quarks. The weight of the Sun, the mass that holds the planets in their orbits, is dominated by energy.
The mass of every star you see in the night sky, every galaxy, every large-scale structure in the observable universe, as far as ordinary matter is concerned, comes mainly from the energy of the strong force binding quarks and gluons together inside protons and neutrons. You are a being whose mass is almost entirely energy, not in some mystical or vague sense, in a precise, quantitative, experimentally verified, computationally confirmed physical sense. The energy of the strong force, the energy of massless gluons zipping between quarks, the energy stored in one of the most powerful interactions in nature, that is what gives you weight. That is what makes you feel heavy when you climb stairs. That is what gives you inertia when a bus suddenly brakes and your body lurches forward. You are not so much made of stuff as you are made of energy, held in patterns that we call particles, which are themselves held in patterns we call atoms, which are held in patterns we call molecules, which are held in patterns we call cells and tissues and organs and bodies. At every level, the mass that makes these structures physical, tangible, and gravitationally significant comes predominantly from energy, not from the intrinsic mass of the most fundamental building blocks. And that energy is not an illusion. It's real. It's measurable. It has consequences you feel every moment of your life. It's just not what we assumed mass was. We assumed mass was the amount of stuff. We discovered that mass is something deeper, something more subtle, something that can emerge from the interactions of massless particles, from the tension of fields, from the dynamics of forces, from the sheer energy packed into the tiniest volumes of space. The universe didn't build you by stacking up material like bricks in a wall. It built you by trapping energy in configurations so stable they've persisted for billions of years. The protons in your body were formed in the first moments after the Big Bang, and they've been carrying their strong force energy ever since, unchanged, for nearly 14 billion years. That energy became atoms. Atoms became molecules. Molecules became the chemical machinery of life, and life eventually became you. A conscious being whose mass is overwhelmingly energy, wondering where mass comes from. We've now seen two of the three pieces of the full picture. Elementary particles get their mass from the Higgs field. Composite particles like protons get most of their mass from the energy of the strong force. But we haven't yet pulled these pieces together into a unified understanding. We haven't asked what this all means for how we should think about mass as a concept. Because here's the deepest question. If mass can come from field interactions for elementary particles and from bound energy for composite particles, then what is mass really? Is it a substance? Is it a property? Is it something built into particles, or something that emerges from relationships and dynamics? And what does it mean for the physical world that the thing we call mass, the thing that gives objects weight and inertia and gravitational pull, can exist without any internal material at all? Those are the questions we'll address next, because the full answer transforms not just how we understand mass, but how we understand what the universe is made of at its most fundamental level. We've now seen two very different mechanisms that generate mass in the universe. For elementary particles like electrons and quarks, mass comes from their interaction with the Higgs field, a field that fills all of space with a non-zero value and gives particles inertia through coupling, not through filling them with material. For composite particles like protons and neutrons, the overwhelming majority of their mass comes from the energy of the strong force, the energy of massless gluons and high-speed quarks and quantum fluctuations, all of it confined inside a tiny volume and manifesting as mass through Einstein's equivalence of energy and mass. Two different mechanisms, two completely different physical origins, and yet both produce the same thing. Mass. Real, measurable, physical mass. Mass that resists acceleration. Mass that responds to gravity. Mass that curves space-time. The universe doesn't care how the mass was generated. Once it's there, it behaves the same way regardless of its origin. This is where we can finally pull everything together and confront the deepest version of our original question. Not just where does mass come from, but what is mass? What kind of thing is it? And what does it tell us about the nature of reality? Let's start with what mass does, because that's where physics is on its firmest ground. Mass has two effects that we can measure with extraordinary precision. The first effect is inertia. A massive object resists changes in its motion. The more mass an object has, the harder it is to accelerate, to slow down, to change direction. This is what Newton captured in his second law of motion. Apply a force to an object and it accelerates by an amount inversely proportional to its mass. Push on something heavy and it barely budges. Push on something light and it flies. This resistance to acceleration, this stubbornness, this tendency to keep doing whatever it's already doing, that's inertia. And mass is the measure of it. The second effect is gravity. Mass generates gravitational attraction. Every object with mass pulls on every other object with mass. Newton described this in 1687 in his law of universal gravitation. Two masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. The more mass you have, the stronger the gravitational pull you create. Einstein deepened this picture dramatically in 1915 with his theory of general relativity. In Einstein's framework, gravity isn't a force in the traditional sense. It's a consequence of the geometry of space-time itself. Mass and energy curve space-time. They warp the fabric of the universe, bending the paths that objects follow. A planet doesn't orbit a star because an invisible force is pulling on it. It orbits because the star's mass has curved space-time in such a way that the straightest possible path through curved space-time happens to be an orbit. The planet is following the natural contours of warped geometry. Here's what's crucial for our story. General relativity doesn't care where the mass came from. It doesn't ask whether the mass originated from the Higgs mechanism, or from strong force energy, or from any other source. It doesn't distinguish between mass that a point-like electron carries because of its coupling to the Higgs field, and mass that a proton carries because of the energy trapped inside it. All of it curves space-time. All of it creates gravity. All of it generates inertia. The physical consequences of mass are identical regardless of the mechanism that produced it. This is actually built into the mathematical structure of general relativity. The source of space-time curvature in Einstein's equations is something called the stress-energy tensor. This mathematical object describes the distribution of all forms of energy and momentum in a region of space. It includes rest mass, kinetic energy, pressure, stress, electromagnetic energy, strong force energy, everything. General relativity adds it all up and curves space-time accordingly. It makes no distinction between different origins of energy and mass. It treats them all equally. This means a kilogram of mass energy from the Higgs mechanism curves space-time exactly as much as a kilogram of mass energy from the strong force, which curves space-time exactly as much as a kilogram of pure electromagnetic radiation. Mass, his mass, his mass, as far as gravity is concerned. The universe is democratic about it.
Whatever produces energy or mass, that energy or mass gravitates. Now let's think carefully about what this means for our understanding of what mass really is. For most of human history, mass was treated as a substance. It was the quantity of matter in something. More matter, more mass. Less matter, less mass. This view dates back at least to Newton, who defined mass essentially this way in his Principia. He called it quantity of matter, and described it as arising from the density and volume of a body. This definition treats mass as though it's something physical, something tangible, something you could, in principle, scoop out of an object and weigh separately. It equates mass with stuff. This definition worked beautifully for 3 centuries. It works perfectly for engineering. It works for building bridges, launching rockets, designing engines, calculating orbits. At the scales where humans operate, mass and stuff go together so reliably that treating them as the same thing causes no problems. But we've now seen that at the deepest level, this equation fails. Mass is not stuff. Mass is a property. It's a measurable quantity that particles and systems possess, not because of what they're made of, but because of how they interact with fields and how energy is configured within them. The electron has mass not because it contains material, but because it couples to the Higgs field. The proton has mass not primarily because its quarks are heavy, but because energy is trapped inside it by the strong force. In both cases, mass is something that emerges from relationships and dynamics, not from substance packed into a container. This is a genuine conceptual revolution. It's as significant as the shift from geocentrism to heliocentrism, or the shift from Newtonian absolute space and time to Einstein's relative spacetime. It changes what we mean by one of the most basic concepts in physics. Think about what property means in this context. Color is a property of objects. A red ball has the property of redness. But redness isn't a substance inside the ball. You can't open the ball and pour out the red. Redness arises from the way the ball's surface interacts with light, absorbing some wavelengths and reflecting others. The property is real, measurable, and has physical consequences, but it's not a substance. Mass works the same way. It's a property that particles have because of how they interact with certain features of the universe, specifically the Higgs field and the dynamics of binding forces. The property is real. It's measurable with extraordinary precision. It has profound physical consequences, determining how objects move, how strongly they gravitate, how space-time curves around them. But it's not a substance you can extract. It's not something stored inside a container. It's a property that emerges from interactions and energy configurations. This doesn't make mass any less real. This is an important point that needs emphasis, because when people hear that mass isn't stuff, they sometimes conclude that mass must be fake, an illusion, a trick of mathematics. That conclusion is completely wrong. Mass is as real as anything in physics. It's one of the most precisely measured quantities in science. The electron's mass is known to 11 significant figures. The proton's mass has been measured with extraordinary accuracy and reproduced from first principles using lattice quantum chromodynamics calculations on supercomputers. These aren't illusions. These aren't mathematical conveniences. These are real physical properties of real physical entities. The electron genuinely resists acceleration. The proton genuinely curbs space-time. You genuinely feel the gravitational pull of the Earth, a pull created by the mass of trillions upon trillions of protons and neutrons, mass that comes overwhelmingly from strong force energy. Saying mass is a property rather than a substance doesn't diminish it. It deepens our understanding of it. It tells us that the universe is more subtle, more elegant, more surprising than our macroscopic intuitions suggest. Now let's address something we've been careful about throughout this story, but that deserves explicit discussion. When physicists say elementary particles like the electron are point-like, what exactly should we make of that? Should we picture the electron as a literal mathematical point, a zero-dimensional object with absolutely no spatial extent, existing at an exact location in space? The honest answer is that we don't know for certain. The statement that the electron is point-like is an experimental statement. It means that in every experiment conducted so far, down to the smallest distances probed by the most powerful particle accelerators, the electron shows no evidence of internal structure or finite size. It behaves in every measurable way as though it's a point. But experiments always have limited resolution. We can only probe down to a certain scale, and below that scale, we simply can't see. It's entirely possible that at even smaller distances we can't currently access, the electron might reveal some kind of structure. Some theoretical frameworks suggest exactly this. String theory proposes that what we observe as point particles are actually tiny one-dimensional strings, vibrating at frequencies that determine the particle's properties. These strings would be extraordinarily small, roughly the Planck length, about 1.6 times 10 to the negative 35 meters. That's roughly 20 orders of magnitude smaller than a proton, far beyond the reach of any current or foreseeable experiment. If string theory is correct, the electron isn't truly a point. It's a tiny vibrating loop or strand of energy. But at every scale we can currently probe, it looks like a point because the string is so incomprehensibly small. Other theoretical ideas propose different kinds of substructure. Preon models suggest quarks and leptons might be built from even more fundamental particles. Various approaches to quantum gravity suggest that at the Planck scale, the very nature of space and time changes so dramatically that concepts like point-like and extended might not apply in the usual sense. These are all open questions. They represent the frontier of fundamental physics, the boundary between what we know and what we don't. The Standard Model, our best current theory of particle physics, treats fundamental particles as point-like, and this treatment works spectacularly well. But the Standard Model is almost certainly not the final word. It doesn't include gravity. It doesn't explain why particles have the specific masses they do. It doesn't tell us why the electron's coupling to the Higgs field has the particular strength it has. These values are measured experimentally and put into the theory by hand, not derived from deeper principles. This is one of the deepest unsolved problems in all of physics. Why does the electron have the mass it has? Why does the top quark interact with the Higgs field roughly 340,000 times more strongly than the electron? The Standard Model doesn't answer these questions. It can't. The coupling strengths between each particle and the Higgs field are free parameters. They're numbers that the theory accepts as inputs, but doesn't predict. You measure them in the laboratory and plug them in. The theory then works beautifully, predicting countless other quantities with extraordinary precision. But the mass values themselves remain unexplained. This is like having a theory of music that perfectly describes how different notes combine into chords and melodies, but can't explain why a piano has the specific set of keys it has. The theory uses the keys brilliantly. It just doesn't derive them from anything deeper. There are roughly 24 such free parameters in the Standard Model. The masses of the 6 quarks, the masses of the 3 charged leptons, the masses of the W and Z bosons, the mass of the Higgs boson itself, along with mixing angles and other constants. All of these are measured, not predicted. Nobody knows why the universe chose these particular values. This is not a failure of the Standard Model. It's a signpost pointing toward deeper physics. The fact that these parameters exist and remain unexplained tells us that the Standard Model, for all its spectacular success, is not the final theory. Something deeper must exist. Some framework that explains why the Higgs field couples to different particles with different strengths. Why there are 3 generations of matter particles and not 2 or 7. Why the masses span such an enormous range, from the nearly massless neutrinos to the extraordinarily heavy top quark. Finding that deeper framework is one of the great quests of modern physics. It might come from string theory. It might come from some other approach we haven't yet imagined. But the mystery is real, and it's telling us something important. We understand how mass arises. We understand the mechanisms. But we don't yet understand why the specific values are what they are. The universe has chosen its parameters, and we don't know why. A truly complete theory, a theory that unifies quantum mechanics and gravity and explains the values of fundamental constants, might reveal that what we call point-like particles have structure at scales we can't yet probe. Or it might reveal that the concept of spatial extent doesn't even apply at the most fundamental level. That the question of whether a particle has size is simply the wrong question to ask. Some approaches to quantum gravity suggest that at the deepest level, space itself is not the smooth, continuous fabric we imagine, but something discrete, something granular, something that only looks smooth and continuous when you zoom out far enough. In such a framework, asking about the size of a fundamental particle might be like asking about the color of a musical note. The question assumes categories that don't apply. What we can say with confidence is this: at every scale we've been able to probe experimentally, fundamental particles behave as point-like objects with definite masses, and those masses come from interactions with fields rather than from internal composition. Whether deeper structure exists at inaccessible scales is an open and fascinating question, but it doesn't change the central insight. Mass does not require being made of stuff. Let's broaden out now and think about what this entire picture tells us about the nature of the physical world. Because the implications go far beyond just understanding the mass of electrons and protons. The universe, at its most fundamental level, is made of quantum fields. These fields fill all of space and time. They're always present, always active at some quantum level, always capable of being excited into the ripples we observe as particles. What we call matter, the solid, tangible stuff of everyday experience, is actually patterns of excitation in these fields. An atom is a specific configuration of excitations in the electron field, the quark fields, and the gluon field, all interacting with each other and with the electromagnetic field and the Higgs field and the other fields of the Standard Model. A molecule is a more complex pattern. A cell is a vastly more complex pattern. A human body is an extraordinarily complex pattern of field excitations. But at bottom, that's what it is. The mass of these patterns comes from 2 sources we've now explored in depth: the intrinsic masses of the elementary excitations, determined by their coupling to the Higgs field, and the energy bound up in the interactions between those excitations, dominated by the strong force inside protons and neutrons. Both sources produce the same kind of mass that resists acceleration and generates gravity. Both are real, both are measurable, and neither requires the massive object to be a container filled with smaller material. This means the distinction between matter and energy, a distinction that feels so fundamental in everyday life, is not as sharp as we thought. Matter isn't a category opposed to energy. Matter is a form of energy. Or, more precisely, what we call matter is a set of stable patterns in quantum fields, patterns that carry energy and therefore carry mass. When you hold a rock, you're holding a pattern of quarks and gluons bound together by the strong force inside protons and neutrons. Those protons and neutrons bound together inside nuclei by the residual strong force. Those nuclei surrounded by electrons bound by the electromagnetic force. Those atoms arranged into a crystalline structure. At every level, the pattern is held together by forces, and the energy of those forces contributes to the mass you feel. This perspective dissolves several confusions that plague popular discussions of physics. People sometimes ask whether matter can be converted into energy, as if they're different substances that can be traded like currencies. The answer is that they were never different substances to begin with. E equals mc squared doesn't describe a conversion between two different things. It describes an equivalence between two measures of the same thing. Mass is a form of energy. Energy has mass. When a nuclear reaction releases energy, the total mass of the products decreases because some of the bound energy that was contributing mass has been released as radiation or kinetic energy. But nothing was converted from one substance to another. The bookkeeping just shifted from one column to another. People also sometimes ask whether particles are real or just mathematical abstractions. This confusion often arises from the unfamiliarity of quantum field theory. When physicists describe particles as excitations of fields, as ripples in abstract mathematical structures, it can sound as though they're saying particles aren't really there, as though the electron is just a math trick, a convenient fiction that makes calculations work. This is wrong. Particles are physically real. When an electron strikes a detector, it produces a real signal. When electrons flow through a wire, they create a real current that powers real devices. When protons collide at the Large Hadron Collider, the debris from those collisions triggers real detectors that produce real data. These are not mathematical abstractions. These are physical events involving physical entities. What's changed is our understanding of what those physical entities are at the deepest level. They're not tiny billiard balls, they're excitations of quantum fields. But excitations of quantum fields are real things. A wave in the ocean is real, even though it's not a separate object from the water. A sound wave is real, even though it's not a substance distinct from air. An electron is real, even though it's an excitation of the electron field rather than an independent little marble. Saying that particles are field excitations and that mass is a property rather than a substance isn't saying the physical world is less real than we thought. It's saying the physical world is differently real than we thought. The universe is built from fields, interactions, and energy patterns, rather than from tiny solid building blocks. But the fields are real, the interactions are real, the energy patterns are real, and mass, the property that emerges from all of this, is absolutely real. Let me bring this home by returning to where we started. You picked up an object. You felt its weight. You felt mass. And you assumed, reasonably, that the mass came from stuff packed inside. Now you know the full story. The object is made of atoms. The atoms are mostly empty space, with tiny nuclei surrounded by electron clouds. The electrons have mass, but they're point-like, with no known internal structure. Their mass comes from their coupling to the Higgs field, a field that fills all of space and is never zero. The nuclei contain protons and neutrons. The protons and neutrons each contain 3 quarks held together by gluons. The quarks have small intrinsic masses from the Higgs field, but those masses account for less than 2% of the proton's mass. More than 98% of the proton's mass comes from the energy of the strong force, the energy of massless gluons and fast-moving quarks and quantum fluctuations, all trapped inside the proton's tiny volume and manifesting as mass through E equals mc squared. The weight you feel when you hold that object is overwhelmingly the gravitational response to strong force energy. The resistance you feel when you try to push it is overwhelmingly the inertia created by that same energy. You are interacting through the simple act of holding a cup of coffee with one of the deepest truths in modern physics. Mass doesn't require stuff. Mass requires energy and field interactions, and the universe provides both in abundance. You yourself are made of the same ingredients. Your body contains roughly 7 billion atoms. The protons and neutrons in those atoms carry mass that is dominated by strong force energy. The electrons in those atoms carry mass from the Higgs field. Your total mass, everything you weigh on a scale, comes from these two mechanisms, and almost none of it comes from the intrinsic mass of the quarks that are supposedly the building blocks of your matter. You are not so much a collection of stuff as you are a pattern of energy and field interactions. A pattern that eats, breathes, thinks, dreams, and wonders where mass comes from. A pattern that has persisted in various forms since the protons in your body were forged in the first moments after the Big Bang, carrying their strong force energy with them for nearly 14 billion years, through generations of stars and supernovae and the slow accretion of planets, until that energy ended up in you, standing on the surface of the Earth, feeling your own weight, and finally understanding what that weight actually is. This is one of the great achievements of modern physics. We've answered a question that goes back to the ancient Greeks. What is mass? Democritus thought mass was the unavoidable consequence of having indivisible material building blocks. Newton thought mass was the quantity of matter in a body. For centuries, those answers were good enough, but they were incomplete. The real answer, the answer that quantum field theory and quantum chromodynamics and the discovery of the Higgs boson in 2012 have given us, is far more surprising and far more beautiful. Mass is a property that emerges from the interaction between particles and fields, and from the energy bound up in the dynamics of forces. It doesn't require internal substance. It doesn't require spatial volume. It doesn't require smaller pieces packed inside. A point-like electron can have mass because it couples to the Higgs field. A proton can have mass that vastly exceeds the mass of its constituents because energy is trapped inside it by the strong force. And both kinds of mass curve space-time, create gravity, and resist acceleration in exactly the same way. The universe isn't made of stuff in the way we always assumed. It's made of fields. It's made of interactions. It's made of energy organized into patterns of breathtaking complexity and stability. And mass, that most familiar and tangible of physical qualities, the thing you feel every time you lift a bag of groceries or climb a flight of stairs, is not evidence of substance packed inside objects. It's evidence of the invisible architecture of reality, the fields that permeate all of space, the forces that bind particles together, and the energy that, through Einstein's profound equivalence, becomes indistinguishable from the thing we've always called matter. You started this journey with a simple question: how can a particle have mass without being made of stuff? Now you know. Mass was never about stuff. Mass was always about something deeper. Something that took humanity centuries to discover, decades to confirm experimentally, and that still has open questions we haven't yet answered. But the central insight is clear. Mass is not the amount of material in something. Mass is a property of fields and energy. And the universe, in all its vastness, in every star and planet and grain of sand, is built from those fields and that energy, including you. The next time you feel your own weight, the next time you push against something heavy, the next time gravity pulls you firmly toward the ground, remember what you've learned. That feeling isn't stuff pulling you down. It's the Higgs field and the strong force and the curvature of space-time, all working together, giving you the mass that makes you real and present and physical in a universe made not of substance, but of something far more remarkable. Fields, energy, interactions, and the mass that emerges from all of them. There's something worth sitting with for a moment before we part ways tonight. The universe didn't have to be this way. There's no obvious reason why mass should work like this. There's no obvious reason why a field should fill all of space with a non-zero value and give otherwise massless particles the property of inertia. There's no obvious reason why the energy of massless gluons should account for nearly all the mass of everything you touch. The universe could have been simpler. It could have been built from little solid blocks, each with a fixed mass, stacking up neatly like the ancient Greeks imagined. That would have been easier to understand, easier to picture, easier to explain. But instead, the universe did something far more interesting. It built mass from relationships, from interactions between particles and fields, from energy trapped in the tension of forces, from the invisible architecture of quantum fields that fill every point in space and never switch off. The universe chose elegance over simplicity, depth over obviousness, and the result is a physical world that is, at its foundation, more beautiful and more strange than anything our ancestors could have imagined. You are part of that strangeness. Every atom in your body carries mass that comes overwhelmingly from the energy of the strong force. Every electron in every atom of your body has mass because it's interacting right now, at this very moment, with the Higgs field that fills the space you're sitting in. You don't feel these interactions, you can't detect them with your senses, but they are happening constantly, sustaining your mass, keeping your atoms together, making you a physical being in a physical universe. The weight you feel in your bones when you stand up after sitting for a long time, the effort it takes to carry something heavy up a flight of stairs, the gentle pull you feel when a car rounds a curve. All of that is mass. And all of that, every bit of it, comes from fields and energy, not from stuff packed into tiny containers. You are not made of stuff. You are made of something more remarkable. You are made of fields interacting, energy binding, forces confining, and patterns persisting across billions of years. You are the universe doing something extraordinary with nothing more than energy and mathematics and the silent, invisible, ever-present fields that make mass possible. And the next time you hold something in your hand, something heavy, something solid, something that feels like it's made of real material, remember what you've learned. That feeling of substance, that sense of solidity, that experience of weight, it's all real. But underneath it, underneath everything, there are no tiny balls of stuff. There are only fields, only energy, only the deep architecture of a universe that found a way to make mass without making stuff. That's the answer. And it's more extraordinary than the question ever suggested.